second function that we are going to be looking at this year is called the exponential function. Its two rules that we're going to look at today is y is equal to c to the x and y is equal to ac to the x. But before we even look at this function, it's super important that we go over some rules of exponents that I hope you can remember. My first question for you is, do you remember how we can change the square root of x into x to the power of some exponent? Well, if you recall, the square root of x is simply x to the power of 1/2, or more specifically, our square root of x to the 1 is equal to x to the 1/2. You'll notice that all we've done is the denominator of our fraction is the root, and the numerator of our fraction is the exponent that goes over the x. So by doing this and by knowing this, we can come up with a general rule that states any base a to the power of a fraction m over n is just equal to the root of n over a to the power of m. So the denominator becomes our root and our numerator becomes the exponent over our base. And this whole thing is rooted. So remembering this rule here in the corner, a to the m over n is equal to n root a to the m. Try some examples. So here I have two examples. I have the fourth root of 34. Now 34 alone, remember that there's an imaginary 1 exponent that I didn't put. And over here we have the cubed root of negative 9 in brackets to the power of 8. So how can we change this into an exponent using this rule up here? So in this case, remember, this here is just the denominator of our fraction, our fractioned exponent, if you will. And the imaginary 1 here is just the numerator of that fraction. So the fourth root of 34 to the power of imaginary 1 is equal to 34 to the 1/4. These two things are equal to the same thing. And on the bottom here, our cubed root of negative 9 to the 8, well, this, remember, is just the denominator of our fraction, so here it is. And this exponent here is the numerator. And our negative 9 in brackets stays in brackets. Nothing changes. The sign does not change in this case. The only thing that changes is what the exponent is. One more exponent rule that you need to remember. This exponent rule will help you solve what 2 to the power of negative 2 is without a calculator. So do you remember what you have to do when you have a negative exponent? A hint is that you don't want a negative exponent, so you're going to have to make it into a positive. So do you know what to do? Well, if you remember, 2 to the power of negative 2 is just 1 over 2 to the power of positive 2. Anytime you see a negative exponent, tell yourself, negative exponents are bad. I do not want a negative exponent. It's too complicated. Let me just flip it and make it into a fraction, and suddenly my exponent becomes positive, and that's way easier. So if I have 2 to the power of negative 2, I say, no, I don't want a negative exponent. Let me flip it, and then the 2 exponent becomes positive. So 1 over 2 to the power of 2 is just 1 over 4, because 2 to the power of 2 is 4. And 1 over 4 is a lot easier to solve because it's just 0.25, and that's it. So 2 to the power of 2 is 0.25, and if you don't believe me, you can check on your calculator. That's what it is. Okay, so in general, if we have to write this rule out, it would be any base a to the power of a negative m is equal to 1 over a to the m. So again, you have a negative exponent, bad, don't like it. Let me flip it, let me make it into a fraction, let me put it over 1, and let me change my exponent into a positive. So much easier for me. So remembering this rule here in the corner, let's try some examples and try not to use your calculator, please. So you have 2 to the power of negative 4, negative 2 to the power of negative 2, and our negative 2 is in brackets here, very important, and 5 to the power of negative 4. So without a calculator, just try and figure out how we can make the exponent positive. So if we check our answers, I have here 1 over 2 to the power of positive 4, because all I did here is say, no, do not want a negative exponent. Let me put it over 1 and change my exponent into a positive. Super simple. Becomes 1 over 16, which if we then use our calculator, it just becomes 0.0625. Our negative 2 to the power of negative 2, it's very important. Our negative 2 in brackets stays in brackets. The only thing that changes is our exponent, and it changes into a positive once we put it over 1. And that's easy because then we just get 1 over 4 because our negative 2 is in brackets. If it wasn't, it would have been a negative 4. 1 over 4 is just decimal 25. And finally, we have 5 to the power of negative 4 again. Negative exponent, bad, bad. So let me put it over 1 into a fraction, change my exponent into something positive, and I get 1 over 625, which if I then use my calculator becomes 0.0016. So now that you should be comfortable with these two exponent rules, let's start by introducing the exponential function y is equal to c to the x. So you are used to seeing functions where x is the base, x squared, x cubed, and the exponent is a number. But in this case, x, our coordinate x, is the exponent, okay? C actually tells us if the function is increasing or decreasing. So remember our function properties. Here is a graph, it's an exponential function, and if we read it from left to right, it is increasing. In this case, because it's increasing, c is greater than 1. In our second example, from left to right, our graph is going down, it is decreasing. When c is between 0 and 1, it's decreasing. So if c is 0.5, 0.25, 0.000009, our function is decreasing. Please note, very important, that c is never equal to 1. It's not greater than or equal to, less than or equal to, because c should never and won't ever be equal to 1. So how do we find c? Where do we get it from? Let me give you an example. Here's a table of values. So my x is going up by increments of 1, 0, 1, 2, 3, and my y is going up by increments of something different. So if we look at our y coordinates, it's going from 1 to 3 to 9 to 27. You should note that it's basically going times 3, times 3, times 3. Also known as times c, times c, times c. When x is increasing by 1 unit, so 0, 1, 2, 3, 1 unit, y is multiplied by the same number each time in an exponential function. We call this number c. So in this case, c is equal to 3. So the rule for this table is simply y is equal to 3x. Here are some facts about y is equal to c to the x. The domain is the set of real numbers, all set of real numbers, and the range is also the set of all real numbers, positive real numbers. The initial value is 1. As we can see here, it is 1. The function has no zeros because it never touches the x-axis, which we will talk about in a second. And the function is positive over that set of real numbers because it never crosses the x-axis. It is always positive. An asymptote is a line that a curve grazes but never touches. In this case, in our exponential function, the x-axis is the asymptote of the curve y is equal to c to the x. So here is our function, and it looks like it's touching the x-axis, right? But I'm telling you that if you zoom into it, it should never actually be on the x-axis. There's always a tiny space between the x-axis and our function. So now you know most of the properties. You also know that there's always an asymptote. We're going to add a parameter a, and we're going to change our function into y is equal to a c to the x. Here is what you're used to. You're used to a being the slope and b being your initial value, or where it crosses the y-axis. With the exponential function changes, your a is actually your initial value, where the function crosses the x-axis, the y-axis. And your b is the slope, but we're not going to talk about b today. We're just going to focus on a. So in an exponential function, a is the initial value. I am terribly sorry for this confusion. I know you're going to get confused, but don't worry. Hopefully we'll get through this. So knowing that, if c is greater than 1, so increasing, these are functions that can tell you where and what a is. So here, the green one crosses 2, so a is 2. Here, the gray one crosses 1, so a is 1. And here, the orange one crosses 0.5, so a is just 0.5. So in all these cases, we can see what a is just by where it crosses the y-axis. In the example where your function is decreasing, so c is between 0 and 1, in this case 0.25, again, you can easily see where it crosses the x-axis, and that is how you identify what your a is, where it crosses. If a is negative, we can assume that it goes below the x-axis, so underneath it, right? Because it has to cross the negative point on the y-axis. So take a positive c, so it's actually increasing, although it's hard to see. But you're just going to have to remember what a negative a c greater than 1 graph is. In this case, my c is 3, so it's increasing. And we can see that the orange one crosses at negative 0.5, the gray one crosses at negative 1, and the green one crosses at negative 2, and that's what my a is going to be. In my second case, using c as 0.25, it's actually a decreasing function. And again, it's hard to tell that it's decreasing because our function is upside down. It's going to be easy if you just memorize which one of these is increasing and decreasing. And again, we can still see where the graph crosses the y-axis, and that is what our a's are going to be. So how about you test yourself? Here are two graphs. And based on the slide before that can help you, can you tell me if a is positive or negative, what exactly a is by looking at where it crosses the y-axis? And can you tell me if c is either an increasing, so c greater than 1, or a decreasing between 0 and 1? In the first case, a is positive because we are above the x-axis. And in this case, we can tell that it's 1 because it's crossing 1 on the y-axis. And if we go from left to right, we can assume and agree that the function is increasing. So c must be greater than 1. The second graph is below the x-axis. So a is definitely negative. And more specifically, it's negative 3 because we see where it crosses here at negative 3. Now, c is a bit tricky. It's hard to tell if a function like this is increasing or decreasing. But if you look at the slide before, you will be able to see that a function that looks like this is actually decreasing. So c is between 0 and 1. It must be a decimal. Now, how do you find the rule? This is the major question for all of our functions. How do you find the rule of your function? The first step here, given this graph, is remembering that a is the initial value of the function. So in this graph, can you see where the function crosses the y-axis? Well, yes, you can. Here's 0, 0.25. So it crosses the y-axis at 0.25. So then a is simply 0.25. So already we have one part of our rule. All we're missing now is our c. Using the same graph and knowing what a is, we need to find c. How do we do this? Well, you are given a second point, 4, 4. So x is 4, y is 4. Using what we have learned, y is equal to 0.25 as a, c to the x, and the 4, 4, we can solve for c. Try it on your own first, and then move on to the next slide. Again, we have to solve for c using that 0.44. All we have to do is take our function y is equal to 0.25 c to the x and put in our coordinates in the equation. So we get 4 is equal to 0.25 c to the 4. Now we want to get the c to the 4 alone because we want to isolate c. So we divide both sides by 0.25 and you should get 16 is equal to c to the 4. Now what? What can we do to figure out what c is when we have our exponent 4? We know that when we have c squared, we square root it. But what do we do when our exponent is not a square? If you didn't know this already, your calculator should have a symbol that looks like this. So it's basically the root of x, any root of any number. On your calculator, you should type in 16, then this symbol, then 4, and then the equals. So you would basically be doing 16 fourth root equal to, and you should get the answer 2. C is equal to 2. And if we check our work, 2 to the power 4 is in fact 16, and therefore C is equal to 2. Let's review. We found A by looking at the initial value of the graph. We found that it crosses at 0.25. We found C by using the other point given, 4, 4, and entering it into the rule y is equal to 0.25 c to the x. We solved for c after plugging that in and using a cool tool on the calculator, the x root tool. So finally, our rule is y is equal to 0.25 2 to the x. Your last turn, using this exponential graph on the right, can you figure out the rule of the function? Remember that the general rule is y is equal to ac to the x, so it is your job right now to find what a and what c is using these 2 points. Pause this video and try it yourself before moving on to the next slide. First, where does this function cross the y-axis? Well, we see that it crosses at 0, negative 2.5. So A is negative 2.5. So already, check, that one's done. So what we're left with is C. We have a second point. It is 1, negative 7.5. So using this rule here, with A as negative 2.5, we take our 1 and our negative 7.5, and we place them into our rule. Very simply though, our c is to the power of 1, so it's just c. So all we're left to do here is isolating c, and we divide both sides by negative 2.5, and we get that c is equal to 3. Therefore, our rule is y is equal to negative 2.5, 3 to the power of x. Remembering that c is the only thing that is to the power of x. A cool note though is that you could have just found c by using the multiplicative factor. So in this case, I gave you 0 for x and 1. And I gave you that y is negative 2.5 in this case and 1 is negative 7.5. And if we can deduce what they're being multiplied by, it is in fact by 3, and that is c. So what is the reason for these parameters? Word problems. It is a lot easier for you to solve word problems if you understand the parameters A, C, and eventually we're going to talk about B. This will be on another PowerPoint. So I hope that you learned as much as you could about exponential functions for now, and we will move on to more complicated stuff in the next PowerPoint.